just me talking at a blank screen for a long time. Okay, we're recording. Hi. So the purpose of this lecture is to show you how you can take ideas you know already about parametric equations, x as a function of time, y as a function of time, and also vector equations, like x and y vectors, and extend it into 3 dimensions. And you can go back and forth very fluidly between those 2 different ways of thinking, and both are useful. Before we do that, let's just agree about what we're going to label things and words we're going to use for the different directions. So if we're in 2 dimensions, I'll refer to the x directions as left and right, and the y directions as up and down. If we're in 3 dimensions, I'm going to try and use north and south for what used to be like the y-axis up and down. And I'll refer to east and west for what used to be the x-axis. And then up and down will really be like above the ground. So you can think about this as being like the ground plane, and then this would be like up in the air or below the ground. Okay, it's going to be helpful to practice sketching in 3D, which is tricky. Not just useful for this class, but in calculus, there's a couple of units where you do stuff in 3 dimensions, and it's really helpful if you can sketch like boxes and cylinders and basic shapes in 3D. So let's give it a try. I don't know if I have good advice. I'll try it, and then if you guys have better advice for how to do this, I'll let you share. You'll get 2 shots at this, at least on this sheet of paper. So go ahead and draw a vertical line, and that'll be like the up-down z-axis. And then instead of drawing a completely horizontal line, you'll draw a line that crosses approximately in the middle and isn't quite horizontal. And then the last step, I feel like you just have to sort of feel it. The last step is you make another one. I guess if you imagine a horizontal line, I've drawn one that's sort of symmetrically reflected above this imaginary horizontal. And you can add your little arrowheads. And let's call this x and y and z. Give a second try. Sketch it again, just for practice. It's also helpful. Let's add some tick marks. When you're adding tick marks, try and make the lines be parallel to, so as I go along the x-axis, these little line segments, I'm trying to make them parallel to the y-axis here. And if I want to extend it, you should try this as well. Extend it with like a little dotted line. If I want to imagine a plane that's cutting across the x equals 2, you can draw some lines straight up that are going to be parallel with the z-axis here. And then you can do another one across that's supposed to be parallel with the y-axis. So I think the trick for sketching in 3D is, to the best of your ability, whenever you're drawing lines, try and make them parallel to whatever axes you've already drawn. See, that looks, I would say, not wholly terrible. I think that looks pretty good, actually. Okay, so let's get to the math part. So 3-dimensional vectors work just like 2-dimensional vectors, but with one more dimension. So 2-dimensional vectors, you use these triangle brackets, and you have an x-coordinate and a y-coordinate. 3-dimensional vectors, same thing, you just have a third coordinate that's your z-coordinate. So, for example, this vector means you go, what did I say? East by 1, north by 10, and up by 3. So if I was going to try and plot this point in 3 dimensions, let's see how I can do it. So this is x, this is y, this is z. So I said it's it's east by 1. So here's 1 unit that way. It'll be 10 units north. So this is not going to be to scale, but it's 10 that way, it's 1 that way, and then it would be 3 straight up. So 1, 2, 3 would be approximately there. And again, it's like real hard to tell what's happening, but that's approximately where it would be. All the math that you know about vectors applies to 3-dimensional vectors just the way it applies to 2-dimensional vectors. So if you have a scale factor on the outside, you can think about that as multiplying each of those distances separately. So 2 times 1 means change in 2. 2 times 10 means change by 20. So you can think about scaling vectors by scalar amounts, just the same. So let's practice imagining some three-dimensional paths that are defined by vectors. So here, the x coordinate is a function of time, the y coordinate's a function of time, and the z coordinate's a function of time. So I'm going to pause the video, decide with your neighbors. You don't have to sketch it if you don't want to, but decide where is this vector pointing at time 0, where is it pointing at time 1, and then go ahead and try and write your own vector here for part B, and then we'll look at answers in like 3 minutes. Go. I have started the video again. Let me unfreeze it. Okay. So figuring out where it is, you can literally just plug in time the way that we do. So if I plug in 0 for t, the x coordinate becomes 0, y coordinate becomes 0 plus 2, which is 2, z coordinate becomes 1 plus 0, which is just 1. So that's time 0, it's there. At time 1, I plug in the times and it evaluates to be 142. I didn't sketch what that looks like here, but I'll show you a way you can look at it in GeoGebra in just a second. For a 3D vector equation that goes through this point at time 1, this one I did try and sketch. There's a lot of them that do it, but I thought the simplest one is, let's just have it be 4t, 10t, 3t, because then if you plug in t equals 1, it just becomes 4, 10, 3, which is what we want. At time 0, it would be at the origin. And so that's what I've sketched here. Time 0, we're at the origin. At time 1, it's gone 4 this way, 10 that way, 3 that way. Again, it's not really to scale. And it's like a little janky, but the purpose of the sketching is just to help you try and visualize the rough path that it's going to take. Okay, before I show you GeoGebra, let me point out, here we have written it in a vector form, but remember this first component tells you your x coordinate, y coordinate, z coordinate. So an equivalent way of writing this same path would be parametrically, using 3 equations. I could say x as a function of time is just t, y as a function of time is 2t plus 2, z as a function of time is 1 plus t. And so sometimes it's going to be easier to think about like your z coordinate as a function of time without even thinking at all about the xy position. Like you can just think about what's my height as a function of time and write that separately from everything else. And then if you can get your path for x and y, then maybe you can combine it all together. But keeping in mind that you can go back and forth between these two different ways of thinking, I think is potentially going to be useful for some of these rides. Okay, so here's GeoGebra. I have a whole handout about this, but the idea is, you see here on the left, I've defined a curve where x is t, y is 2t plus 2, and z is 1 plus t. So that's that part A that you just did. And you can click and drag it around, and so you can see at time 0, it's there, and at time 1, it's here. So this is really helpful for being able to visualize your paths. You can't click inside this and have it do anything helpful. So I've defined f and g of h up here to represent the x and the y and the z. So it's like you would type it. So if I wanted to change it, so let's do like t plus 5. And so now I've just added 5 to the x coordinate. So now it starts, whoops. So now you can see the red axis is the x-axis. So you can see it starts at 5 and goes up from there. So if you want to change it, you would change it with x and y and z separately in these 3 equations. And then this is the curve that's based on those equations that actually sketches. And then I also have like a little cube down here for reference. All right, we're back. So if we're going to write... Sorry to interrupt you. If you're going to write a 3D vector equation that starts at the point 4, 10, 3 and hits some other point sometime later, this equation has nothing to do with that, seemingly. I'm just reminding you of a thing we've done in the past. So way back in Unit 2, we had this pattern where you can start with a vector here that's not being scaled by anything. And then you have a time-scaled vector. So if time is 0, I'm scaling this by 0, and my position is just this first vector. So that's why you can think about this as my position at time 0. It's like my starting vector. And then from my starting location, I'm going to add a time-scaled vector that's pointed in the direction I want to be moving. So that general idea, you can just apply directly to this three-dimensional case. And let's see if I can just do it right away. So at time 0, I want to be at 4, 10, 3. And then I'm going to have a time-scaled vector that's pointed from this point to that point. So I have to think if I'm going to go from 4 to 5, that's like an increase by 1 in the x. If I'm going to go from 10 to 12, that's an increase by 2 in the y. If I go from 3 to 3, that's an increase of 0 in the z. And so this is now going to be a vector that does what we want. How could I visualize it using GeoGebra? Let's go back to GeoGebra. So you'll notice GeoGebra doesn't let me type in a nice vector equation like this. GeoGebra wants me to type in a parametric equation where x and y and z are separate. So let's remember, again, how you can go back and forth between them. You can simplify out all the x components. So here's an x, and then remember t is being multiplied into all three of these. So if I was going to rewrite this, I could rewrite it as, I guess I'll do it in 2 steps. So step 1 will be 4, 10, 3 is the same. And then I'll multiply the t in. So this is now t, 2t, 0. And then as the second step, I'll add component-wise. So the two x's would get added together. So I'll have my x of t equation is 4 plus t. My y of t equation is 10 plus 2t. And my z of t equation is just 3 because z doesn't actually change with time because my time-scaled vector has 0 for its z component. So the point here is you can think about it conveniently using vectors, but then sometimes you'll need to combine all of the x's together to write it parametrically, and then you can visualize it in GeoGebra. All right, let's flip the page over. Circles. All right, so let's pretend, wow, it's really unclear what axes I was trying to achieve here. So write a 3D vector equation for a circular motion in the YZ plane. So the YZ plane means even though it looks like my circle is sticking out into the X region here, that's my bad. This is supposed to be all the points around the perimeter of this circle are all supposed to have an X coordinate of 0, which means they're neither to the right nor the left. They're neither north nor, or they're neither east nor west here. Hopefully you can sort of imagine that. Take a minute with your neighbor. If the radius of this circular motion is 10, fill in the 3D coordinates for all 4 of these points: lowest, middle, highest, middle, lowest. All right. So, apologies for my bad pictures. So the x coordinates are all supposed to be 0. And like you can see that, actually you can see that pretty clearly on these 4 points, because these 4 points, you can see them intersecting the axes here. So let's start with this point that's kind of back this way in the y-axis. So the x coordinate is 0 because it's neither east nor west. The y coordinate, the radius was 10, so the y coordinate is 10 in this direction. And the up-down coordinate, the z coordinate, is 0 because I'm right on the y-axis here. The z coordinate up here is going to be 10 because I've gone 10 up. The x is 0, and it looks like the y is also 0 because I'm neither north nor south. I've just gone directly up from the origin. So it's 0, 0 is the origin, and then I've gone up to make it 10 above. This one should be 0 for the x, negative 10 for the y, 0 for the z. Straight down from the origin, you've got 0, 0 for the x and the y, and then negative 10 is the height, because I'm going down from the origin. So again, these basic exercises are just trying to help you get used to looking at a three-dimensional, like a poorly drawn three-dimensional thing. Could we take this? Oh, let's write the equation for the circular motion. That was the whole point of this. Okay, so in 2 dimensions, a circular motion would be cosine t sine t, where it's like this was x and this was y. So take a minute and think. Think with your neighbors. One of these three things is just a number, and you should know what number it is. One of these things is going to be a cosine and one's a sine. So think it through and try and decide what you think makes sense to you. So all the coordinates on this circle, all the x coordinates on this circle are 0. So it's pretty safe to put a 0 there because I know as I move around, I am never going east or west. I'm never leaving that YZ plane. I like to think of it this way, and you can tell me if you have a different way of thinking about it. Imagine standing here looking at it this direction. So in that case, the y-axis here would be sort of sticking out to the right as I'm looking at it from this way. And the z-axis is kind of going up. So in my imagination, I'm thinking about this as x and this as y. It's like I'm holding a piece of paper in front of me. And that circular graph would have like x, y axes, right? So that will tell me which axes I should treat like x and y from the familiar graph before. So if I have a familiar xy circle, which axis in my 3D is acting like the x? It's this y-axis. So I'm going to take my cosine t and make it be my y position. And then the up-down axis, which used to be y, in 3D is z. And so I'm going to do the sine t that used to give me my y coordinate and make that my z coordinate. So this is going to give you a nice three-dimensional circular motion in the yz plane. Could I shift it east by 3 and up by 12 so that it's centered somewhere else? I mean, this is the power of vectors. So east by 3, there you go. I'm not shifting it north or south at all. I'm shifting it up by 12. So that's like I now have this vector that's pointing here to the center. And onto that, I can add the vector that defines my circular motion. Cosine t, sine t. So it all works the same as in 2 dimensions, just with a third dimension. And then again, if we wanted to write out our equations parametrically, we would just collect the x and the y and the z together. So the x coordinates now are always 3. The y coordinates are 0 plus cosine t, which is just cosine t. The z coordinates are 12 plus sine t. So you can go back and forth between those two different representations. An excellent point. My Ferris wheel is not big enough. This is a unit length vector, so I would need to multiply the whole, I'd need to scale the whole vector by 10 because the radius was 10. Thank you very much. So we'll do that here, and do that here, and do that everywhere. This x does not get scaled by 10 because the 3 came from the shift here. But this is 10, and then that would be 10. All right, other questions or suggestions? Corrections, as it were. All right. Yes. All right, I'm going to give you a minute. Give this a try. So we could rewrite these parametrically as a vector this way. So I could say my position is t0. What's that going to look like as time goes from like 0 up to 1, let's say? So try and sketch it in 3 dimensions here, sketch this in 3 dimensions, sketch this in 3 dimensions. Go. So I've started the video again. Here's GeoGebra. Let's actually just look at these in GeoGebra. So here's x is time, y is time, but z is going to be 0. So hopefully you predicted that that is a diagonal line with a height of 0 that just goes from the origin out to this point at 1, 1. Okay, so what happens if we take that exact line and we make the height be t squared? So if you have a squared term, that's going to be sort of parabolic, and hopefully this is what you imagined. And something that's nice about this is you can like look directly down the axes. So here I'm looking down the the xz plane. So you see a parabola that way. And if I look down the yz plane, there's also a parabola that way. So it's sort of this parabola that's going sort of diagonally. And, you know, if we wanted to, we could look at, let's look at sine t. Oh, let's scale this differently. Let's do 2 pi. So now I've got a sine function, but it's a sine function that is, like, the sine function is describing the height, but again, in the ground plane, it's headed diagonally. Okay, video going. Let's look at number 3. So x is a function of time, it's just t. Y is going to be sine 2 pi t. Whoops. And then z is going to be time. So if you look at what's happening,